Hello everyone, I am Dr. Siddheshwar Chopra and today we'll learn about the consequences of Lorentz transformation equations, primarily the length contraction and time dilation today. We start with the length contraction. One of the consequences of Lorentz transformations is length contraction. A rod's length is the greatest when it is at rest relative to an observer. So that is the main concept we have to understand. So we define a system of the frames and the rod again. You can see here in the diagram. Let a rod be placed in the S dash frame parallel to the X dash axis, and S dash is moving with velocity, constant velocity v along the plus x axis. Let its endpoints be at x dash and x dash 1 and x dash 2. So these are the endpoints of the rod as measured in S dash frame at the same instant of time, and hence its proper length is given by L naught is equal to x2 dash minus x1 dash. So please pay attention here. The rod is effectively at rest with respect to the S dash frame, and the coordinates of the rod are x2 dash and x1 dash with respect to the observer O dash in S dash frame, and this length is called as proper length because the rod is effectively at rest with respect to O dash observer. So this length is called the proper length, and V is of the order of C. So now we continue. It must be noted that L0 is the length of the rod measured in a frame in which it is at rest. So that is very important to understand. Its endpoints are measured to be x1 and x2 in S at the same instant of time, and hence its length with respect to S, that is improper apparent or relativistic length, will be x2 minus x1. So the observer O, which is measuring the length of the rod, such that the frame itself is moving at a very high velocity, which is of the order of c, then that measurement of the length will be termed as improper apparent or relativistic length, isn't it? Because that observer is measuring the rod from a very far distance because V is almost of the order of C. So this is apparent length x2 minus x1. Now we use Lorentz transformation equations. We have these equations with us. These are again direct equations here, which are x1 dash is equal to x1 minus vt by root of 1 minus v square by c square. X2 dash is equal to x2 minus vt by root of 1 minus v square by c square. So now what is your proper length? That is L naught, which is equal to x2 dash minus x1 dash. So let us substitute these Lorentz transformation equations, or I should say direct Lorentz transformation equations, in the proper length formula, which is x2 dash minus x1 dash. We get this equation, x2 minus vt by root of 1 minus v square by c square minus x1 by minus vt by root of 1 minus v square by c square, which vt gets cancelled out. So I have x2 minus x1 by root of 1 minus v square by c square. Now let me substitute x2 minus x1 to be L, and on the left hand side I already have L naught, which is x2 dash minus x1 dash. So I get my length contraction formula, which is L is equal to L naught root of 1 minus v square by c square, which implies L is less than equal to L naught. So it shows that when a rod moves with a velocity v relative to the observer, its measured length is contracted by a factor of root of 1 minus v square by c square in the direction of motion, whereas its direct dimensions perpendicular to the direction of the motion remain unaffected. So only in the direction of the motion, as it was seen in the Lorentz-Fitzgerald contraction hypothesis also, that only in the direction of the motion the length contraction is visible. This effect is called length contraction. So this effect is visible for the observer, which is at rest in the inertial frame S. So next we go to the time dilation. It is another consequence of the Lorentz transformation equation, which says that a clock is measured to go at its fastest rate when it is at rest relative to the observer. So basically in the diagram you can see, now let us place a clock in S dash frame at a fixed distance x dash. So everything is visible in the diagram. You can see it here. So we have placed a clock now in frame S dash and at a distance x dash with respect to observer O dash, and S dash is moving with the constant velocity along plus x axis. Let there be two ticks of the clock T1 dash and T2 dash. So now I am considering, in the previous length contraction case we considered the length of the rod, so two measurement points x1 and x2 dash were considered. Now in this case I am considering two ticks of the clock T1 dash and T2 dash as measured in S dash, and let's say duration of an event in the S dash frame is given as T2 dash minus T1 dash. So this is just difference between these two events, which is given by T2 dash minus T1 dash. Again V is almost of the order of C. So now since the clock is at rest in S dash frame, this time interval T2 dash minus T1 dash is called proper time. So however, the duration of the same event with respect to S frame is T2 minus T1, which is called improper apparent or relativistic time. Please understand this, because this is the measurement made with respect to the S observer who is far away from this clock. So this time is called the improper apparent or relativistic time. Now in this case I use inverse Lorentz transformation equations wherein I can have the unprimed quantities, which are T1 and T2, as T1 dash plus Vx dash by C square by root of 1 minus V square by C square, and T2 is T2 dash plus Vx dash by C square by root of 1 minus V square by C square. You may ask, why did I use the inverse Lorentz transformation equations? Because on the right hand side you see here x dash factor is coming into picture and x dash is fixed. So straight away, if I were to find what is T, which is the relativistic time, that is T2 minus T1, straight away these factors get cancelled out, which are the Vx dash by C square factor. So I straight away get T2 minus T1 is equal to T2 dash minus T1 dash by root of 1 minus V square by C square, or T is equal to T naught by root of 1 minus V square by C square, wherein you see here time gets dilated. T is equal to greater than equal to T naught. T is basically greater than equal to T naught, and T is the time measurement made by the observer O in frame S. So that is why you see the time has got expanded, dilated for this observer. So above equation shows that when a clock moves with velocity v relative to the observer, its rate is measured to have slowed down by a factor of root of 1 minus v square by c square. This effect is known as time dilation. So that's all for this lecture. Thank you.